So this video we're going to talk about the effect of concentrations of reactants on the rate of reactions. As we have mentioned in the previous videos, there are 4 factors affecting the rate of reactions. So this video we're going to focus on the concentrations of the reactants. So to study the effect of concentration of reactants on rate of reactions, we're going to use these reactions to study. So we are putting magnesium into the acid, and in the process we generate hydrogen. So the volume of hydrogen will be measured by the Gaussian range. As we are studying the rate of reactions, we also need a stopwatch to help us. As we are going to comparing different setup, so in the process we have to identify the independent variable, fixed variable, and dependent variable. What we're going to study is the concentration of the reactants. So we are going to change the concentration of the acid in these experiments. So you have to notice that the independent variable for this experiments, it is the concentration of acid. We're going to use, say for example, 1m, 2m, 3m of HCl. Okay, different setup. Okay, we're going to use different molarity acid. But the fixed variable, we have to fix the other variables in order to confirm that the results is due to the concentration of acid but not the other factors. So for the fixed variables that we need, we have to fix the volume of acid that we use, the mass of magnesium that we have added into the acid. Okay, so in the process what we're going to do, we're going to measure the volume of gas collected. Okay, so this will be the results that we're going to look at. So one thing I want to draw your attention is normally the acid that we use will be usually in excess. And actually it's not only in excess but also in a very high concentrations. Because we want to make sure the concentration of acid remains more or less constant throughout the experiment. What means by that? I'm trying to put it in numbers so it will be easier for you to understand. Say for example, we are using 0.1 m HCl, which is 100 cm cube. If I convert this one into number of mole, that will be 0.01 mole. If in the process, this is excess reactant, I have used 0.005 mole, then you will find that it will only have 0.005 mole HCl left. If I convert it back into a molarities, then this one will become 0.05 m capital letter. So what we are having here, it will be reduced by half from the original molarity. Is that right? But if I change the molarity this time, change to 1m, what happened next? If I have 1m this time, and still 100 cm cube, so in the process, this one will become 0.1 mole. If in the process I also use 0.05 mole here, so the remaining number of mole of HCl will be 0.095 mole. So if I convert it back into concentrations, that will be 0.95 capital letter M. So you can see that in this process, the reductions, from 1m to 0.95 m, the percentage is far less than this one. So we will say that 1m and 0.95 m is more or less constant in the process. But if you have 0.1 m decrease to 0.05, which is reduced by half, then we can't say that it's more or less constant. So in the process, normally we will using excess acid, and also we prefer to have the acid at a higher concentration as well. So this is the point that I would like you to remember, why the acid we use is in excess and also at high concentration. So for the results of the experiments, we will find that we can put a product time graph here. So the volume of hydrogen will produce in the process against time. If we have a higher concentration, you can see that it got a steeper slope than a lower concentration one. Not only this, the reaction will end earlier. You can see that here. End earlier. And then this one will end later. So not only we have a less steep slope here. Less steep slope means lower rate, but also, okay, it will be end later if you're using a lower concentration. But for a higher concentrations, that will be a steeper slope. That means you have a faster rate. Faster rate, okay, it will be end earlier as well. So these are the two things I want you to pay attention to. Higher concentration, higher initial rate, and reaction ends earlier. Okay, but one thing very, very important, okay, you can see that, okay, the volume of hydrogen produced, okay, no matter which concentrations, you see that all of them, they have end up at the same amount of volume of hydrogen produced, because this level, okay, you have to remember this level, that is the total volume of product. Actually, this one depends on, okay, depends on the amount of limited reagent. In this case, the limited reagent, because HCl is in excess, in this case, the limited reagent, it will be magnesium. Okay, if we use the same mass of magnesium, then we'll find that, okay, the product, okay, the volume of hydrogen produced should be the same. So in this graph, okay, I just want you to pay attention to higher concentration, higher rate, that means steeper slope, and also the end earlier. Okay, if you have a lower concentration, less steep slope, and later. And also one thing is, okay, no matter which concentration you are having, okay, the total volume of product form will be the same because it will be related to the limited reagent. So if we you can conclude that if we increase the concentration of reactant, actually will increase the reaction rate. So if we want to explain, okay, why higher concentrations, the rate will be faster, basically we can consider this picture. So first of all, okay, this is the concentrations, okay, inside, this is the container. Inside you see that the particles, okay, they are quite far apart, okay. They will just randomly move around in this container. And once they hit at a right orientation, and also at high speed, that is meeting the activation energies, okay, then you have a effective collisions to occur. Okay, this will be directly proportional to the number of collisions that you're going to have. If we have a higher concentration, that means they will be crowded, okay, like this one. Okay, so we will say that, okay, in per unit volume, okay, the number of particle will be more. What means by per unit volume? Say for example here, okay, I just chopped this one into 4 boxes. Average, okay, you'll find that is around 2 to 3 particle here. But for this one, okay, per unit volume, you can see that, okay, it will be like up to 1, 2, 3, 4, 5, 6 particle here. So if in the areas, okay, you got more particles, the collision that you're going to make, okay, normally, okay, it will be higher. We have a higher chance to produce a effective collision. So basically, if you try to explain in terms of collision theory, we'll say like this: when the concentrations of the solutions or the reactants increase, the number of reactant particles per unit volume, this one's very important. Every unit volume, the number of reactant particle, you also increase because concentration increase, right? So the chance to collide, okay, the frequency will increase. And in this case, we'll know that this is the most important part, okay? The number of effective collision, not enough, per unit time, okay? We'll find that this will also increase. That's why the reaction rate will then increase. Okay, so this is normally, okay, a typical questions to ask you to explain using collision theory why concentration increase, the rate will increase. If you want to talk about the concentration decrease, the rate decrease, actually you're using the same model. Concentration decrease, number of reactant particle per unit volume decrease, chance to collide will reduce, and the number of effective collision per unit time get lower, so therefore the reaction rate will decrease. Okay, so this is how we make use of the collision theory to explain the effect. And on the other way round, if we talk about the reactions involve gas particles, we can also consider like this: if we are having gas particles and in the process, okay, we increase the pressure. So this is a container that we have, okay? The number of gas particles are limited, okay, inside this container. But if we increase the pressure, that means the volume decrease, okay? The four walls moving towards each other, okay? So we have a smaller volume. So smaller volume, the pressures will then increase. So in the process, okay, we'll find that the unit of the particles in unit volumes will increase. Number of particles in unit volumes, okay, will then increase. So this one is more or less like increasing the concentrations. So again, this will increase the chance to collide. Number of effective collision per unit time will also increase. So basically, pressure increase, volume decrease, number of particles in unit volume will increase. They are crowded. So chance to collide, okay, more easy for them to collide. Number of effective collisions, okay, per unit time, that is about chances, right? Probability. They will also increase in this case. That's why the rate will also increase. So this is how we use the collision theory to explain, okay, pressure increase, okay, in some of the reactions. So have a look of an examples, okay? So right here, okay, we're going to explain why reaction rate decrease with time for most of the reactions, okay? So the concentration time graph is shown right here. So first of all, you're going to arrange the instantaneous rate RA, RB, RC at ABC, okay, in descending order. So we are talking about instantaneous rate, okay? Recall your memories. We need to draw a tangent at time equals to that one, okay, and then the slope of tangent will then equals to the instantaneous rate, okay. So basically, A, we're going to draw a tangent, B, we're going to draw a tangent, C, we're going to draw a tangent. You see that A, this one, okay, have to be the steepest slope, okay. So this one is the least steep. So therefore, we'll find that descending order, okay, it have to be, okay, RA the highest, okay, and then go to RB and then go to RC, okay. So explain the change in reaction rate with time. As time goes by, okay, at the very beginning, this one is a very important question, okay, I have to highlight this one, okay. So at the very beginning, okay, we will notice that the concentrations of the reactant should be the highest. Concentration highest, that means, okay, the number of particles in unit volume, it have to be highest. Is that right? Number of particles in unit volume highest. And if it's like this, the collisions, okay, will increase. And the number of effective collision per unit time will also increase. That's why, okay, the rate is higher when it is at the beginning. But as time goes by, what happened? Okay, as time goes by, okay, the reactions, okay, the concentration of the reactants, okay, will be decreasing. And finally, the reactant will be used up. So we'll find that, okay, when the concentration drops, okay, number of particles will go down, collision go down, number of effective collisions will also go down. So therefore, the rate will be decreasing, okay. Of course, you will see that, okay, if we have to answer all these things, that will be a very lengthy paragraph. So right now, okay, we just focus on the question, explain the change in reaction rate with time. Why the reaction rate will change? Because the concentrations of the reactant change. Okay, how does it change? It decreases. So basically, you can say that, okay, at the beginning, what happened to the concentration? As the reaction proceeds, what happened to the concentration of the reactants? Okay, and then at the end of the reaction, what happened to the reactants? So if you mentioned, okay, all these changes in the reactants, okay, concentration of reactants, then you can relate that to the rate, okay. So you can see that, okay, as the reaction proceeds, reactant is being used up. So you can find that the concentration decrease in the process. And at the beginning, or at the end, okay, the reactant is used up. So therefore, the reaction stops and the rate becomes zero. Okay, so this is some typical questions that we may come across, okay, in the public exam. So I have another examples. So graph below shows a curves, okay, reactions involving same mass zinc strips, excess dilute hydrochloric acid. So one thing you have to pay attention to, same mass. That means same products. Okay, if we change the HCl, the concentration of HCl, you're talking about changing the excess chemicals. Okay, so therefore it won't change the amount of the product. So in this case, okay, if we are having molarity of HCl, does the reaction take place shortest time to complete at what molarity of HCl? Shortest time, okay, that means fastest rate, okay, fastest rate to complete. So in this case, okay, it is easy. That will be 2.0 molarities, okay, because you can see that they earn earlier, okay. And the second one is the same volume of hydrogen produced in each case, okay. You have to tell them that, okay, because we are using same mass zinc strips, okay, in the process. That will be the limited reagent, so therefore it will have the same amount of products, okay. And the last one, okay, you're going to sketch a curve which have 0.1 HCl. 0.1 HCl comparing to 0.5. 0.5 and comparing to 0.1. 0.1 is a lower concentrations. So therefore we have a lower rate. Lower rate means less steep slope. So the first one that we're going to draw will be a less steep slope, and they will end later, okay, than this one. Is that right? Later. So therefore we have this slope and then we end later. So the whole graph, okay, will be like this way. Okay. Second question, okay, when we have two magnesium ribbons of the same mass added separately to 50 cm3 2m HCl and 50 cm3 2m ethanoic acid. So what is the difference here? Okay, so the focus have to be, one of them is strong acid, one of them is weak acid. So weak acid tell you that, okay, they will be partly ionized, okay, or partially ionized. So the concentration of H plus here will be relatively lower than the concentration of H plus in the HCl. So which reaction takes place at a shorter time? Shorter time means faster rate. Okay, so we'll know that, okay, faster rate, it should be talking about HCl. Okay, so here you try to explain HCl and also ethanoic acid. One of them is strong acid, one of them is weak acid. And right here, it will be related to, most important, the H plus concentrations that is different, okay, between HCl and CH3COH. HCl has a higher concentration of H plus. So the key point is we know that, okay, rate increase with the concentration of the reactants. So therefore the one between, okay, the hydrochloric acid, okay, will be faster and take a shorter time. Okay, so second part, okay, do these reactions, okay, produce same amount of hydrogen gas? We have to check which one, okay, is a limited reagent. So this one, okay, will be 2 times 0.05. So you have 0.1 m for the acid. So both of them are the same. And the other one is 0.1 gram mg. So if 0.1 gram, we found that the number of mole of mg is 4.12 times 10 to negative 3. If we do the maths, okay, 1 mg need 2 H plus to react, okay. So this one, okay, actually we need 4.12 times 10 to negative 3 divided by 1 times 2. So we just need 8.24 times 10 to negative 3. That means 0.00824. But what we need, or what we have here, we have 0.1 mole already. So that means that, okay, the Mg is a limited reagent. Okay, if Mg is a limited reagent, in both cases, actually we have the same mass of magnesium. Okay, same mass of magnesium. That means that, okay, the product, okay, will also be the same. Okay, so you can have a look of the answers. Okay, amount of acid is in excess. Okay, and magnesium is a limited reagent. Same mass of magnesium. Okay, so therefore same amount of hydrogen gas produced. Okay, so bear in mind, amount of products Okay, it will depend on the amount of limited reagent all the time. So in this case, we just need to identify which one is limited reagent, okay, and then we can find out the answer. So last practice, okay, this one is talking about decrease in concentrations. Okay, how will it affect the rate? So basically, again, decrease the concentrations, number of reactant particle per unit volume will decrease, chance to collide will decrease, number of effective collision per unit time will also decrease, and reaction rate will then increase. Okay, so these kind of questions, okay, if very simple, okay, not comparing two chemicals, okay, then you can explain in details. But like previous ones, say for example HCl versus ethanoic acid or things like that, then in that limited mark, okay, you may not need to explain that much. Okay, so it really depends on the question types and also the mark allocations. If you think that you need a more detailed one, okay, this process or this flow, okay, have to be used. To summarize the videos, okay, we have learned that to study the effect of concentration of reactants on rate of reaction, we can use a setup like this. And in the process, we are changing the concentrations of the acid or molarity of the acid. Okay, and we have to keep the volume of acid and mass of magnesium the same. What we're going to measure is the volume of gas produced. And we have to learn that, okay, we may need to sketch another curve. That means if I give you 1 m, you may need to sketch 2 m or 0.5 m like this way. So the effect is if we have a higher concentrations, we'll notice that, okay, there will be a higher initial rate. Okay, higher initial rate, and also they will end earlier. Okay, so same amount of product. This one really depends on the amount of limited reagent. In this case, okay, we are having the acid, okay, as an excess reagent. So even you increase the concentration, it won't change the amount of product. Okay, very important thing is you have to explain with collision theory. These two are typical flows, okay, to explain, okay, how the concentration change, okay, and will affect the reaction rate eventually. So the one on the left hand side is talking about the concentration change. The one on the right hand side is talking about the pressure change or volume change to a system, include gas products, okay, or gas particles. Okay, so basically, okay, that will be what we have learned in this video. That's all for this video. Bye bye.